Okay, so we'll finish up talking about psychoacoustic methods, and then we'll move on into discussion about the article, the adaptive procedures for hearing aid prescription article, and then we'll try to finish up the signal detection theory lecture, because that's kind of pretty short one. There's only a couple pages on it in the text. Last time we finished up talking about the simple up-down method, and that's talked about in greater detail in that article that you guys read. But for the simple up-down method, essentially we're looking to converge on the 50% point on the psychometric function so that we can get an estimate of threshold. We can see there's a sample up here on the screen on that figure, or in the figure on the bottom portion of the slide, where when you get positive responses, you simply go down by whatever your predetermined step size is. When you get negative responses, you go up. So pretty similar to what we do in clinical audiology. The main difference is our step sizes are different for audiometry, going down versus up, but similar idea overall. So we can see that each run, and the run is defined by the number of trials prior to a reversal. Once we have a reversal and the direction changes, we start a new run. You can see the numbering schematic on the screen reflects that. So we have number 1 where we're going down, second run we're coming up, third run going down, fourth run we're going up, fifth run going down, sixth run going up, etc. So there are modifications of this particular procedure for other purposes, to look at other points on the psychometric function. Some key things about this particular procedure would be that if you, actually I think I'll also mention some about the step size. The step size can change. It doesn't have to be fixed for the entire protocol. You could have the step size start out to be larger and then cut it down to a smaller step size after so many runs in order to try to maximize efficiency. One area of bias that can be introduced with this particular procedure is subjects might pick up on the fact where if they respond correctly, that it changes direction, or if they respond incorrectly, it changes in the opposite direction. Because it is a very simple algorithm, it wouldn't be terribly surprising for the subject to pick up on how it's operating, and to have some biases superimposed on top of it because of that, because of their expectations. We already talked about anticipation bias, and so that could certainly be introduced here if the subject realized the algorithm being used. There we go. So let's move on to another type of procedure to determine threshold. This is a kind of a different animal altogether. It's called the PEST procedure, parameter estimation by sequential testing. In the text here, they really only talk about one version of the PEST test, but there are actually multiple versions of this test. The particular one they talk about in the test is used to home in on the 50% point on the psychometric function, I believe. And in this particular version, there are a certain set of rules here. And those rules are predicated on the fact that each subject's response will result in lowering the stimulus level, whereas a lack of response, correct response results in lowering the stimulus level, and an incorrect response results in raising the stimulus level. So that part is very similar to what we talked about with the simple up-down method. But the part that's different is these set of rules here, which is going to have an impact on step size. Step size will start out larger and get smaller and smaller and smaller. So it's usually after each reversal, and so basically each new run after reversal is when we typically have a change in the step size. So we double the step size if we get a negative response on 2 successive presentations in the same direction, and we half the step size if we get a single positive response. So it's set up in such a way that you're more likely to be going down, as opposed, or more likely to be doubling the. No, let me rephrase that. It's set up in a different way than the other procedures are. So because we keep cutting down the step size, once we get more positive responses, we're probably going to get a pretty good resolution, or pretty precise measure in the end. Because if we're cutting down from, say, 4 dB to 2 dB, then 1 dB, and depending on the system, you could cut down to a half dB with a certain setup. But if you were using an audiometer, 1 dB would be the finest resolution you could have. And then your stopping criteria could be a variety of things. It may be that you have a predefined number of runs, or you could stop based on when you reach some certain level of precision. So let me see if I've got a figure. Here's a figure representing an example of the PEST protocol here. What we can see with this particular setup is we've got stimulus or trial A. The first trial, it's a negative response, so we go up. Second trial, negative response, go up again. And the first two have the exact same step size. Those are arbitrary units, but going from C to D, we double the step size because we had 2 negative responses. Because there was no response on A, and there was no response on A, so they went up. No response in B, went up again, and then no response on C, and then they doubled the step size there. And then if we get one positive response, we're supposed to be halving the step size. And then if we move from E onto F, it looks like we got 2 negative responses, and then we ended up halving the step size. I'm sorry, 2 negatives should be doubling the step size. Yeah, 2 negatives would double the step size. And then for each positive, we're having it. This didn't look like, to me, it didn't look like it matched up perfectly with the description here, but maybe I'm missing something there. But the general idea behind the PEST procedure is that it's very efficient. It's going to be able to determine your threshold with a minimal number of trials, and that you can achieve a good deal of fine precision or good precision because you're constantly having the step size. So when you're using these larger step size in the beginning, you're trying to home in on roughly where that threshold is, and so you can do it fairly quickly because you're using large step size. And then as you cut down with the step size, you're able to get a more precise measurement. So with an intensity resolution of maybe 1 dB or even a half dB. So we talked about the simple up-down method, efficacy tracking method, talked about PEST, and now we'll be talking about the block up-down methods. So these are kind of all variations on a lot of the same thing. These are all kind of, in one way or another, a lot of these are variations of that simple up-down method. I guess the efficacy tracking isn't quite a variation of that, but they all have various things in common. For the block up-down method, we're not really looking to well, we could look at other points on the psychometric function. For this block up-down method, we're pretty much not going to be using the 50% point because we could use the simple up-down method for that. The block up-down method is a modification of that simple up-down method where we're trying to find out what the 75% point is on the psychometric function, or the 80% point. And your rule would change depending on which particular point in the psychometric function you're interested in. So if it were 75% as an example, then you'd want to have this 3 out of 4 rule, where stimulus intensity is going to be increased whenever there are less than 3 out of 4 correct in a given block, and decreased when all 4 are correct. If you wanted to change it to the 80% point, then it would be 4 out of 5. You just modify that rule slightly to 4 out of 5. So it would be stimulus intensity is raised whenever there are less than 4 out of 5 correct responses in a block, and decreased when all 5 are correct. So you can see it's just filling in the blank, changing the parameter slightly. And so then that particular procedure, your stopping point is when 3 out of 4 are correct for the 75% point on the psychometric function, or if you're looking at the 80% point, it would be when 4 out of 5 correct responses are obtained. So here's an example of it, and there's 2 versions of it they describe in the text: the block up-down temporal interval forced choice procedure, that Bud-TIF, and basic versus the Bud-Yen blocked up-down yes-no procedure. Not really the most memorable acronyms or names for these things, but the difference between the two is pretty straightforward. With that Bud-TIF model, you're using the 2-interval force choice, where you've got interval 1, and there's some kind of light might come on to signal to the subject that they need to listen during that first interval, and then interval 2 comes on, and the light comes on to signal they need to listen, and then they choose which interval the signal is present in contrast to the Bud-Yen, which would be the yes-no paradigm, where there's only one interval. It's a 1-interval force choice procedure, where there's the light that comes on to let them know that the interval is present, and they say, yes, I've heard the signal, or no, I have not heard the signal present. And the benefit of that Bud-TIF, or really any 2-interval force choice procedure over that simple yes-no procedure, is that you're able to get a measure of a false positive rate or false alarm rate. You can track that, or a guessing rate. You can kind of track that. But we can see in some ways this looks a lot like the simple up-down procedure. The main difference is we're blocking things. When we talked about the simple up-down procedure, you have a positive response, you go down, you have a negative response, you go up. Here, it's the same idea. You have a positive response, you go down, negative response, you go up, except instead of talking about single responses, we're talking about a block of responses here. And here would be, the example we see on the screen here represents that 3 out of 4 rule with a 75% point on the psychometric function. So we can see they've got 4 correct, 4 correct, 4 correct, 4 correct, keep going down, and then they get 4 incorrect, and then you go back up, and you keep going back up until we get to the 3 out of 4 correct. So we never got to you can see that we never had 3 out of 4 at any other point in this experiment so far. We had 100%, 100%, 100%, 100%, 0, 25, 50, 100, 75. So here we keep going until we get a 75% correct response.
So how long between each stimulus?
How long between it? Oh, okay. So you mean the timing, you mean. The interstimulus interval varies depending on the study, but it might be something along the lines of maybe a half second or something like that. But it's pretty brief, but it's not too terribly brief. And those are pretty standard. I'd have to double check to see if that's the exact number, and that may vary a little bit from study to study. But I think the main thing with the interstimulus interval is it's a compromise between, if it's too long, then you may, depending on the type of study, say for example you were looking at to establish a differential threshold, and for intensity or frequency or something like that, if you had too long of an interstimulus interval between the tone that's being modified versus the comparison tone, then the one of them may escape your auditory memory, right? The comparison tone, you may forget what it is. So you don't want it to be too long, and also that'll increase the duration of the whole procedure, which you don't want to do that either. But you don't want it to be too short either, because you don't want to give the person too little time to react. You don't want response time to start interfering with the way they're responding behavior. And then the transformed up-down procedure, and this is again a modification of the simple up-down procedure, and this was talked about in depth by Harry Levitt in the Adaptive Procedures for Hearing Aid Prescription and Other Audiologic Applications article. I believe he is the creator of this transformed up-down procedure, but it's again it's a similar idea to what we looked at before. It's really, in a way, it's kind of blocking, but this particular one is a little bit different. The rule is. So we have this particular one is going to utilize the negative and positive, like a combination. So if we get, I believe on this one, the up rule would be if you get either one negative or a positive and a negative, then you go up in intensity, or if you get 2 positive responses, then you go down in intensity. And so we can see on the, if we just look for a moment on the very top part of the figure where it says 70.7%, we can see if we get a negative response, we go up, negative response, we go up. Let me see my mouse. Negative response, we go up. Positive and negative response, and we go up again because we need 2 positive responses before we go down. Positive, negative, up, positive, negative, up, positive, negative, up. 2 positive responses, now we can go down, and then 2 positive responses again, and we should be going down again. I'm not sure why that looks the way it does. Positive and negative, we go up. Positive and positive, we go down. Negative, we go up. Positive, positive, we go down. It must be a modification of the rule that I was missing here.
And if it's negative, then you would go back.
Maybe am I looking at the bottom part? The bottom should be just the inverse of the top. Yeah, I'm not sure why it's, if we have two positives here, I would have expected we would have gone down like here, but two more positives I would have expected. Oh, I'm sorry. That is right. I don't know what I was thinking. Two positives, you go down. Two positives, you go down. Positive and negative up. Two positives down. Negative up. Positive, positive down. Positive, positive. Yeah, that is correct. I don't know what I was thinking here. And so this is if you're searching for the 71% point on the psychometric function. And the opposite of that here, if you're looking for this 29% point on the psychometric function, the way the rule is set up is pretty much the exact same, except it's completely flipped. So if we have a positive, we go down, or a negative and a positive, we go down, you have to have two negatives to go up. So you can see that the rule is based, if you look at that up rule in your text and down rule in your text on page 154, you just reverse those signs for the up rule and the down rule, and then you're looking at the opposite point, or the inverse, I guess, on the psychometric function there. So one of the reasons why you might look for a different point on the psychometric function, for example, the 71% point on the psychometric function as opposed to the 50% point, would be if you're using specifically a two-interval forced choice procedure. Because what's going to happen if you just have a two-interval forced choice procedure, what are the chances of a person guessing correctly on any given stimulus?
50%.
Exactly. So if it's 50%, you don't want to be searching for the 50% point on the psychometric function. You probably want to be just searching a little bit higher point, so like the 71% point. So here's an example of the some variations of the transformed up-down procedure for estimating various points on the various points other than the 50% point on the psychometric function. So we already talked about that 29% point, and we already talked about the 71%. I was just rounding it up. And then you can also have the rule for a 20% or an 80% point, or 79. These are just kind of the inverse of one another. You can see if these are going to be flipped around here. You have three negatives here, three positives here, and here this is the inverse of right over here. Here it's positive, negative, or negative, negative, positive, and down here it's negative, positive, negative, and positive, positive, negative. So these are completely opposite of one another. So if you already know the rule for one point on the psychometric function, if you want to find out what the inverse is, you just flip it around completely. From what my understanding is, I believe the most popular, from what I've seen at least, is this 71% point for psychoacoustic studies. I think that's the one that's the most common, and Levitt is always referenced in an older one of his papers. He's got tons of references for that, because I'm pretty sure, I don't think they just use that in hearing science and psychoacoustics. I'm pretty sure they use that in psychophysics as well. More generally, I guess, in psychophysics. So if we want to talk about direct scaling procedure, so this is a new category. We're no longer in the adaptive. We're no longer in these adaptive procedures. We're in direct scaling, which is it's different categories. We talked initially about these classical procedures. Remember the method of limits, method of constant stimuli, method of adjustment, and then the adaptive procedures. And now these are direct scaling procedures. So when you think of direct scaling procedures, think of kind of a ratio or an arbitrary assignment of a particular number associated with it. It's kind of like having a reference tone and then saying, oh, this is twice as loud. Or someone might say, adjust the audiometer so it's twice as loud. So a lot of times we're talking about ratios when we're talking about direct scaling. So whereas these classic and adaptive procedures typically involve discriminating small differences between a pair of stimuli, these direct scaling procedures typically ask the subject to establish a perceptual relationship between the two. So what is the ratio between the two, your perceptual ratio between the two? Is it twice as high in pitch? Is it twice as great in loudness? And there are a variety of ways you can do that. We can have ratio estimation and production, magnitude estimation and production. A couple other ones we'll talk about in a little bit, but really the two classical ways, or really this would be four, I guess, four classical ways of direct scaling: ratio estimation, ratio production, magnitude estimation, magnitude production. So with ratio estimation, what we're talking about is kind of ratios, like I was talking about a moment ago. So when we talk about ratio estimation, the subject is presented with two stimuli sequentially, and they're asked to express one as a ratio of the other. Okay, so they might express one particular sound is a tenth of the, or I'm sorry, twice or three or four times as loud is the reference tone. Ratio production is kind of the same thing, except it's asking the subject to actually control the stimulus, so that instead of the subject saying, okay, that's twice as loud, now the tester is going to say, I want you to adjust the stimulus so that it's twice as loud. So it's just a little bit flipped around there. You're getting at the same thing more or less. The difference would be with ratio estimation that the tester, the experimenter, is determining the two levels or the two frequencies or levels or whatever of the tones, and asking the patient to establish a ratio between the two. Whereas ratio production, the tester is saying, adjust it so that you have this relationship, so that it is twice as loud. So you can see it's a subtle difference between the two. It's a matter of, with ratio production, the subject is adjusting the stimulus so that it is a predetermined ratio, whereas with ratio estimation, the subject is assigning the ratio of preset levels or preset frequency differences. Any questions on that? But so the same kind of difference holds when we talk about magnitude estimation versus production. But the big difference between the kind of the ratio estimation and, say, magnitude estimation is that instead of talking about ratios where it has to be twice as loud or four times as loud or something like that, we might assign kind of numbers off an arbitrary scale, kind of an imaginary scale that has no physical quantity to it. We might say on a scale of 1 to 10, assign these physical intensities a subjective magnitude. So, say for example, say there's a tone being presented, and you want to assign it a loudness rating. You might say it's a 5. On a scale of 1 to 10, it's a 5, 10 being the loudest, 1 being the softest. And you hear another tone, and it's a little bit softer, and you say, oh, that's a 3, on a scale of 1 to 10. So the subject is assigning numbers on a scale provided to them by the tester. The tester will determine if the scale is 1 to 10 or 1 to 100 or whatever like that. The other aspect of this with magnitude estimation is there is an option to have something called a modulus, and this is a reference stimuli or a standard stimuli for purposes of comparison. So if there is a modulus, what will happen is the tester will present this modulus or this kind of comparison tone and say, okay, this is a 5. Use this as your reference point and assign a number to this other tone that I'm presenting to you. So this was a 5 in loudness. Here's another tone. What is it in loudness now on a scale of 1 to 10? No, it's louder, I think it's about a 7, or it's softer, I think it's about a 3. So you get a comparison tone. And then, of course, they're presented with a variety of intensities. There's not just a few trials. There's typically going to be many, many trials to ensure reliability and precision.
Could you give like a 1 and a 10?
What's
Or
that?
just 1? Could you say like this is a 1 and this is a 10? Or would you just have to say this is a 10 or this is a 5 for the modulus?
Oh, you mean having two moduluses?
Yeah, could you do that or no?
I'm not sure, to be honest with you. I don't think they usually do that, but I'm not 100% certain on that. Yeah. Okay, so and the kind of the flip side of magnitude estimation is magnitude production. It's kind of the same difference that we see between ratio estimation and ratio production. So with magnitude production, we see the subject being presented with numbers representing those perceptual values, and then the subject must adjust the actual stimulus. So they have a dial, they have control over the stimulus. They must adjust it on a particular parameter, intensity, frequency, in order for it to match the numbers that were assigned by the tester. So you have maybe you have a modulus of a tone that's a 5 in loudness, and the tester says, I want you to adjust the loudness of this tone until it's a 9. So then the subject adjusts the intensity of the tone until they have a perceived loudness of 9. So here's an example of a graph that shows an example of where the modulus might be. For this particular figure, we see that the closed circles are with a modulus and the open squares are without a modulus. But you see they all fall within this. They're very similar. You don't see a significant difference between the two. They're all clustering around that linear slope of 1. So whether you have the modulus or not, it doesn't seem to make a very large difference. Any questions on this? And this is just a figure with magnitude estimation. So with this one, the tester is presenting tones at a certain frequency or intensity and asking the patient to assign it a number on a scale of whatever, 1 to 10, 1 to 100. This particular one looks like it's on a scale of 1 to 100. So these are some other characteristics about each of these. And these may be, actually these are kind of biases for each of these. So just like there are advantages to each procedure, there are also some drawbacks. With magnitude estimation, one of the drawbacks is that the subjects in the study, in the experiment, will tend not to assign extreme values. So if you have a magnitude scale of 1 to 100, you're not going to have people assigning 1s and 100s very often. They're going to so there's a bias to stay away from those extremes. With magnitude production, when the subject is in control of the dial, they're in control of the intensity or the frequency depending on the type of study. They're not likely to make any dramatic level changes. So they're not likely to go on one particular, say for example, the tone is, say for example, the tester is telling them to adjust the first one to a 3 in loudness and then the next one to a 10 in loudness. They're not likely to make as big of a change between the two because it's they're not likely to make this very, very large change. I guess 1 versus 10 or 1 versus 100, the two extremes of the scale, if they had them sequentially back to back, then you're less likely to see the subject make those large level changes that correspond to the same changes in numbers. And then we also have magnitude balance, where you're taking the geometric mean of magnitude estimation and magnitude production. And the reason you might do that would be to overcome some of those biases. So we already talked about how we take the average. We take the arithmetic average of the ascending and descending trials to help overcome biases in some of those classical procedures. With this one, you might take the geometric mean of, which is a little different than the arithmetic mean, of the magnitude estimation and magnitude production procedures to overcome those biases. So here's a figure. You can see this is a comparison of magnitude estimation and magnitude production. You can see that they primarily have discrepancies between the two for those lower stimulus levels or lower loudness levels, and in the psychological magnitude balance is kind of bisecting those two curves for magnitude estimation and magnitude production, so you can kind of get a reasonable compromise between those two procedures in order to minimize biases. But the obvious drawback to that would be the additional time it takes to conduct the same kind of experiment with two different protocols or procedures. but if in the end it reduces bias, then it may be worth it. And there's another loudness procedure for direct scaling, which is somewhat interesting, called cross-modality matching. This is where you might ask a subject to express what is the magnitude in one sense in terms of another sensory modality. So, for example, I want you to draw a line as long as, to make it as long as you perceive the loudness of the sound. Okay? So the louder the sound is to you, the longer the line you draw. So that would be an example of something you could do. And for cross-modality matching, see, another one you could do would be if, that's probably the one that comes to mind most readily. I think I've seen a paper where they looked at children with a severe to profound hearing loss as a way to handle direct scaling loudness judgments with those children with hearing loss. Because their hearing loss was so severe, I think there was other limitations with these other direct scaling procedures. But it's basically combining two modalities. They're getting the sensory representation in one modality. It could be hearing, and maybe they're expressing it in another modality, say in terms of vision. But I'm sure there's other combinations you could certainly use there that I'm not familiar with. Then category rating of loudness. To me, this seemed awfully similar to magnitude estimation. But I suppose the main difference would be that there's names associated with these. This is the scale like from 1 to 7, where you've got very soft to uncomfortably loud. And this would be like a clinical procedure, the Cox contour test. With that Cox contour test, if you recall, we go from very soft at a 1 to up to 7 for uncomfortably loud. And for that, you're going to have the tester or the experimenter present the tone. And for example, it could be at various intensities. And then the task of the client or the subject is to assign a number to them, which happens to correspond to a descriptor, a linguistic descriptor. So like loud but okay, comfortable but slightly loud, that kind of thing. Okay. Any questions before we move on to the next section? Okay. Okay, let's talk a little bit about the article Adaptive Procedures for Hearing Aid Prescription. Let me pull that up here. There we go. The screen there. Okay. So last time I asked you to please read this one before class today. So this article is kind of to sum it up, went over a lot of these procedures, not really a lot, but it went over the simple up-down procedure and the transformed up-down procedure in greater depth compared to the textbook. And then it also talked about clinical application of the transformed up-down procedure using for word recognition testing, and then other adaptive procedures for the hearing aid prescription. So my first question to you guys would be, did you find that you got any more information in terms of the simple up-down procedure and the transformed up-down procedure compared to the text? Did you get any of your questions answered by reading this one first, or I don't know? Did you guys read this?
The exact same stuff.
Okay.
Yeah.
Were there any points in the text that were kind of unclear that you found clarified here? Not really?
No.
No?
Not really. I think it made it more clear, but I didn't really think it was new.
Okay.
Information was more
There was some redundancy there, but there definitely was some new information as well. Some of the new information, for example, would be the rules, the 4 rules they have in here. At least some of those were new at very least. I think the step size being approximately 1/3 to 1/6 of the transition region of the response curve. I think that was new. I don't think that was in the textbook. but I could be wrong on that one.
I was kind of confused about exactly what transition.
Yeah, the term kind of makes it confusing. So what they're talking about is if you look at, let me see if I have a figure here. We just need a psychometric function to look at, if there is one here. Okay. The fact that this has two curves on it doesn't matter. Just look at one of these curves. So what they're looking at, I believe, is you're looking at, you're not looking at the extremes. If you're looking at, say, 10% positive responses to 90% positive responses, the slope doesn't change dramatically in that region. And so that's kind of what they're talking about. They want to restrict they want to restrict it by looking at that particular range of intensities, if we're talking about intensity, so that we can estimate step size from that. So that's kind of what they're talking about, where they're transitioning from, say, this slope here to up here. So where it's kind of a little bit steeper slope and is fairly constant. And then let's see here. Then they showed a few other rules for that transformed up-down procedure that I put in the PowerPoint. So not a lot of this was terribly new. Yeah, but I was hoping that it would also kind of reinforce the stuff because it was a different author who wrote the paper versus the text. And my opinion on those kind of things is that it's better to read two different authors covering the same material as opposed to reading the same exact thing twice, because there's always going to be limitations in any kind of writing because it's going to be written through the perspective of the author, which is inherently going to be shaped by forces around them, whereas another author will have a different perspective, may not be dramatically different, but at least subtly different, which may help clarify some ambiguities in the writing. But I did like how they talked about using this transformed up-down procedure for estimation of PB max. Can anyone give me kind of an overview of that and talk a little bit about how they use the transform up-down procedure for estimating PB max?
I didn't really get it, honestly.
Okay.
I read over it, I just don't.
Was it more you didn't understand the purpose or the procedure?
I didn't understand the procedure.
Okay. So I know you already know the purpose, but the purpose of it is to figure out what intensity level should we test to achieve PB max, right? Because, so what is PB max?
The best word recognition you can get.
Yeah, exactly. The best word recognition score you can get. So in theory, if we measured word recognition abilities using, the ideal conditions, say 50 words per list, and we measured it at 60 dB SPL, 70, 80, 90, 100, 110 or whatever. You're measuring a variety of levels that we know is not going to happen clinically due to time constraints and due to subject motivation and fatigue. If we were able to measure all of these, that would be great. We would know what PB max is, but we can't measure all of those. So is there a way we can predict what PB max would be? Okay. So I think in the past, I don't remember if it was clinic or a class or maybe Dr. Downs' class, I feel like either myself or Dr. Downs might have told you in the past that on average, fairly recent research has suggested that using the UCL -5 is a reasonable presentation level to achieve PB max for on average. Well, there's variability as well, and so if you wanted to have greater certainty that you've achieved PB max for a given individual, there may be procedures to do that. And Levitt described using this transformed up-down procedure to do that. So if let me scroll down on this paper here and find a figure, an example of the data here. So let's find the rule first here. Let me see where that rule is here. We're looking for positive and negative or negative and positive. Let me go back up here. Okay, so if we get negative followed by positive, then we're going to negative, positive. Then I believe, let me flip down here. I believe we're going to go up in intensity. Is that right? negative, positive. No, I'm sorry. Negative, positive. We go down. Positive, negative. We go up. Yeah, negative, positive. We go down. Positive, negative. We go up. So when I'm saying negative, positive, what we're doing is presenting two words. And he didn't specifically say this, but that was my impression, is that say you've got a PB list, okay, or a phonetically balanced word list, and you present, you're looking for a certain pattern, right? What we should see with the psychometric function, let me go up here, we should see that, that higher intensity levels are going to produce a greater percent of correct responses compared to lower intensity levels, okay? So what we're looking for here, flip down here, we're looking for combinations of negative, positive, like he first gets the first word wrong and the second word correct, and then we're going to go down. If he gets the first one correct and the second one incorrect, then we go up. And then for two negatives and two positives, you simply ignore those and repeat it at the exact same level. If I remember right, these are at two different levels, the presentation. Let me see here. Pause this for a moment. Okay, so the what that's telling us, oh, that's what it is. Okay, I was trying to remember that. I was mistaken. Yeah, so what's actually happening here, so that's what I was looking for. Thank you for mentioning that. What you're actually doing is you're presenting you're presenting two words at different intensities. And those intensities, I believe, are 10 dB apart. And our step size, as an example, was 10 dB in general. So we present one word at 75 and one at 85. And the idea is if we get both positive or both negative, that's not meaningful to us because it doesn't tell us anything about the slope of the psychometric function. What we're expecting to see is that if we want to get a negative response on the lower intensity word, we want it to be incorrect. We want a positive response on the slightly higher intensity word, 10 dB higher, where it is correct, because that is indicative of the slope of the psychometric function here, right? The idea here is that we get the percent correct goes up as we go up in intensity level. So it stands to reason that we would expect to have more correct responses at higher intensities. So what we're doing here is that's why when we get one incorrect, one correct and one incorrect, so this is the pattern we expect to see, we're going up. We're going up because we don't think we've reached PB max yet. But when we get the opposite pattern, say a negative and a positive, then maybe you're worried about rollover here. Okay, then maybe you're too far. Maybe you're on the other side. You've gone too far. Maybe you're on the opposite side of the psychometric function. And so what you're trying to do there is you're trying to get it down to a point where you can average this data and get a predictor of what stimulus level you should use for PB max. So as an example here, let me see how many runs we have here. Well, I think we've got 7 runs, and I believe they discarded the very first run, and that's a common practice to discard maybe the first 1 or 2 whatever runs because they're going to be more variable and less consistent in the data. And so what they did was they looked at the peaks and the valleys. So here's a peak, for example. Here's a valley. Here's a peak. Here's a valley. We look at the peaks and valleys for those 6, I believe, 6. So 1, 2, 3, 4, 5, 6. I think it's the last 6. I think those are. But anyways, look at the intensity levels for those last 6 peaks and valleys. Then we average them. And then we can go ahead and get the level. So the last 6 here, let's see, I wrote that down at here. They've got it listed right here. Yeah, it goes 100, 80, 90, 80, 180. So here, 100, and then down here to 80, 90, 80, 100, and then 80. So yeah, we discarded this here and this here. We discarded those in the beginning, and we averaged the intensity levels for those last 6 runs, the last 6 peaks and valleys, and we end up getting around 88 dB SPL. So you just kind of round up to the nearest 5 dB step size. I mean, you could use 2 dB step sizes if you wanted, but you can round up to 90 dB SPL and present your words there, like a 50-word list at that level. So you're presenting, let's see how many words they actually presented in advance. So 2, 5, 6, 8, 10, 11, 13, we got 17, 19, 21, 22, 20, 23 words prior to actually starting the full list, the list you're going to actually score for an estimate of word recognition abilities, an estimate of PB max. So you kind of did a half list prior to actually doing your real test, and you did that half list in order to estimate what the SPL level should be at for estimating PB max. Now, I'm sure it won't come as a surprise to you. This probably is not widely used at all, but I also suspect that this isn't terribly hard to do in clinical practice if you wanted to, and it probably isn't terribly time-consuming either, especially if you decided you were going to do just a 25-word list at PB max, even though there are some drawbacks to doing that. So it might be kind of like doing 50 words instead of 25 words to begin with. You might add another 2 or 3 minutes. You know, it may take a little bit longer in the beginning because you have to get used to this pattern, kind of like when you first started out with pure tone audiometry. You probably were a little bit slower, a little bit more sluggish with that pattern of up 5, down 10. But after doing it several times, I'm sure you get faster and more proficient until it becomes automatic. So a very interesting way to establish a level to use for PB max. But I haven't seen. It's not referenced very much, let me say that. I checked on Google Scholar because I was curious how often this paper was referenced. The reason I was curious about that would be because that would give me an indication of if, and based on the names of these papers that cited this paper, if this was used widely in an area of research that I was unfamiliar with. It had only been cited about a dozen times, which is a very small number of times considering how old this is. So I don't think it's widely used at all. But it seems like, at least theoretically, to me, it seems like a pretty good idea, a pretty neat thing to try in a research study, or clinically, I suppose. We won't get into the hearing aid aspect of it here because that one was a little bit more complex. But I found this one on applying this transformed up-down procedure for estimation of PB max. I thought that was a pretty interesting way to do it, or a pretty interesting way to apply some of these psychophysical procedures. Any of you guys have any other thoughts on it?
I do have a question.
Mm-hmm.
You said that they presented in 10 dB steps?
Yeah, yep.
So then would the dot be the median between those?
Yeah, that's just the median or the mean intensity level. Yeah. So they just did that for to make it, I guess, more clear. Because if you didn't have the dots there, it would look kind of messier and be harder to follow with the eye. Yeah. Okay, so we're going to talk about signal detection theory, and so this, as short as that chapter was on psychoacoustics, this signal detection theory is even shorter. I do have the syllabus updated, so that article has replaced the other one on the original syllabus, and that's online. The syllabus is the updated syllabus, and I'll be throwing both these PowerPoints online probably right after class. There is an article that I do want you guys to read for next time. It's going to talk about signal detection theory in a slightly different way. Maybe it's a little bit longer, and it's probably going to explain a few things that maybe the book glossed over. Maybe you'll find it completely redundant. I don't know. Could one of you guys, I have an extra copy probably for Natalie, if one of you guys could give a copy to her,
We
maybe.
won't see her till Wednesday.
Today's Monday?
Yeah.
Oh,
But we
okay.
can
She only
It doesn't
learned
matter to
on
me.
Monday.
Yeah, that's fine either way. And it'll be online too.
Okay.
But okay, so yeah, signal detection theory. So we already talked about the psychoacoustic methods, what methods we're going to use to obtain the data of interest. but there are other things to consider. We haven't really talked about how we're going to separate, really separate the signal, the sensitivity, auditory sensitivity or sensory capacity from the response behavior. We haven't talked about that. We've kind of mentioned it, but we haven't really talked about how we can discriminate the two or separate the two. So this was a slide that you saw from the psychoacoustic methods lecture from earlier, where we've got two things that are basically combined together when we're getting responses from our subjects. We have the response is based on both what they're sensing, what they're hearing, kind of a bottom-up, low-level response, and we also have decision processes. So these top-down responses are going to influence their behavior. So here's an example, right? If we have if you give somebody these directions where I want you, say you're doing pure tone audiometry, and you say, I want you to push the button every time you hear a tone, no matter how soft it gets, right? That's one way you could say it. Another way you could say it would be, I want you to push the button whenever you hear a tone, but only when you're certain that you've heard it, right? So what have we done there? We've altered their response behavior. We've altered their response bias. We've altered the criterion they use in order to respond, that internalized criterion. So how do we account for that? Well, that's kind of what the point of signal detection, or one of the points of signal detection theory is as it applies to psychophysics and psychoacoustics. And some of this may actually seem more familiar than you realized if you haven't read this yet. So the first thing would be, if we have a hypothetical experiment where we're asking the subject to, say, have a yes-no paradigm, like a one-interval forced choice or single-interval forced choice procedure. So within each interval, they have to say, yes, I've heard it, or no, I haven't heard anything, like a tone. And there are four possible outcomes here. Either they say, yes, I've heard it, and there actually was a tone, and that would be a hit. They say, no, I didn't hear anything, and there actually was a tone, that would be a miss. Or they say, yes, I've heard a tone, and no, there wasn't a tone. They say, yes, I've heard a tone, and no, there wasn't a tone, that's a false alarm. And, the other one was, no, I didn't hear a tone, and there was a tone would be a miss. And then, yes, I heard a tone, and there was no tone, that would be a false alarm. And no, I didn't hear a tone, there was no tone, a correct rejection. So that should sound familiar to you guys, right? You guys have talked about something like this in clinical audiology, I think. You might have talked about it in terms of sensitivity and specificity, or maybe other terms that he's used. So this is but at least half of this is the same idea. At least half of this is. So the idea is, for a given test, right? For a test, we want to have the greatest number of hits and the greatest number of correct rejections as possible, right? So if we think of the hit rate, that's like sensitivity, and we think of the correct rejection rate, that would be like specificity. And then we could take the hit rate, we could take one minus the hit rate to get the false alarm rate, and we could get one minus the correct rejection rate to get the miss rate. So they're all related typically. So here's an example of the stimulus response table that we just looked at, and there is some data from the text that was filled in. So we have our hit rate was, say, 78%, correct rejection rate was 83%, and you can see that if we take 1 minus 0.78, so minus the hit rate, we have 0.22, which is the miss rate. And if we take 1 minus 1 minus the false alarm rate, that gives us the correct rejection rate, or 1 minus the correct rejection rate gives us the false alarm rate. So you can think of these in terms of ratios or percentages, because it's almost the same thing. And so this is based on the idea that you had a study where about 100 stimuli were presented, or 100 test trials and 100 catch trials. So a catch trial, we didn't talk about that. Maybe we did talk about that. The catch trial is where there's no stimulus being presented. There is intentionally no stimulus being presented so that you can see what their response rate is without any stimuli. You can kind of gauge their guessing rate, or you can kind of gauge their response bias. Any questions so far? Yes. Okay. So the problem is the guessing. Okay, so if we have a hit rate of 78%, like in the example there, we have to really compensate for the guessing. We have to compensate for those false alarms, and so there's a formula to do that. There's a formula to compensate for those false alarms, and this formula could be used to adjust for. To adjust for that the guessing effect. So our corrected rate is going to be the hit rate minus the false alarm rate divided by 1 minus the false alarm rate. And if you input those numbers that we saw in the example here a moment ago, what you're going to see is the actual hit rate is reduced to about 74% or 73.5%. So typically, what we have is the greater the false alarm rate, the greater the correction on the corrected hit rate, or the bigger the difference, and really the smaller the hit rate. The more false alarms, the smaller the hit rate's going to go. But the problem with that is even if we use this formula to help in terms of a corrected hit rate, it doesn't really truthfully allow us to separate the sensory capacity of an individual versus the response behavior. And that's where this aspect of signal detection theory comes in. So what we have here are two probability density distributions. We've got on the top A and B. Well, A and B are both a pair of probability density distributions. We have one distribution representing the noise, which is N, one distribution representing signal plus noise, which is Sn. What's the main difference between the figure A and figure B here? What seems to be the main difference between those two curves?
Peak difference?
Yeah, the separation between the two peaks, right? So on the x-axis, what we can conceptualize here is this is the amount of energy in the noise and the amount of energy, and really the amount of energy. And it holds to reason that if the noise is held constant, that if you add the signal to the noise, it's going to have greater energy, right? If you have the same amount of noise both in the N distribution and the Sn distribution, and you add the signal, which is going to be more energy no matter how slight, it's going to be greater than just the N. And so we can see that on the x-axis here, you can conceptualize this as the magnitude of sensory stimulation, or the magnitude of energy in the signals. Either way you can think about it. On the y-axis, this is just the probability of an event occurring, or the probability of something in the distribution obtaining that value. And so the key here, so I'll get on to what D means in a moment here, but what you can see is that these distributions have greater overlap on the figure B here, less separation between the two distributions. So if we look at that, if we want to understand how do we quantify the separation between the peaks of these distributions, or really how do we quantify the separation of these distributions, there's a measure called D prime. So it's called D prime, but it's written D kind of apostrophe for your accent mark there. What we're really looking at in order to calculate D prime is what is the magnitude of separation between those peaks divided by the variance, or the variability in those distributions. So really we're looking at mean difference divided by standard deviation. So mean difference of these two distributions divided by standard deviation. So if we assume that If we assume that standard deviation, since these distributions in B and A look very similar, except the distance that they are apart from one another, but it's say this distribution here, the SN here is about the same as the SN here at the top one. They have the same width, the same height, right? Those distributions are similar. So they probably have the same standard deviation. They have the same difference between this vertical line and the tail here, the positive tail here. So they have these distributions have the same standard deviation, and probably all four of them do. And the mean difference between this one is larger than the mean difference between this one. It happens to be probably double. So we talked about separation divided by spread. If we have standard deviation is held constant, but we have a larger separation between the two distributions here, then D prime is going to come out to be larger. And we see that here. D prime is 2, D prime down here is 1. So we're looking at the mean difference between the two distributions. Well, we don't have to worry about this being a pooled standard deviation here because the standard deviation seems to be the same for both distributions. And that's oftentimes the case, but if it wasn't the case, you'd probably take an average or pool the two standard deviations together. So this is how we quantify the difference between the distributions. And this is considered a measure that's capable of quantifying sensory capacity or sensitivity without being as heavily affected by response behavior. So if we want to apply what we know about psychoacoustic methods into this signal detection theory, we can change the x-axis. Instead of representing energy or sensory stimulation, you might think of it as a continuum between no responses and yes responses. So the farther on the right you go, the more likely you are to have a yes response. Farther on the left you go, the more likely you are to have a no response. This vertical line represents the response criterion of a given subject, right? I talked about at the beginning how you can tell the person to respond even if they just barely hear the tone. That would be a very liberal or a loose response or lax response criterion. So that would mean that we're shifting it over to the left. We'd be shifting this response criterion over to the left. You can imagine this response criterion here, the vertical line, as being the separation between yes and no. If you have a yes-no paradigm where a tone is presented and the task is to say, yes, I've heard it, or no, I haven't heard it, this is the response criterion. Remember, your directions you give them will impact where is the response criterion. So I said you're shifting it over to the left. That means that they're more likely to respond with a yes if you have a more lax criterion. If you change the wording of your direction, saying I want you to only respond to and say yes if you're fairly certain you've heard it, then you're shifting their response criterion to the right, which means they're more likely to say no more often. Okay? So that's kind of the key factor here, is that you can actually impact the response criterion of the patient with your directions, and this allows you to put it into some kind of model, I guess. So if we want to think about it in terms of energy again, whenever the energy or the stimulation, sensory stimulation, is greater than the response criterion, your response is yes. Whenever it's less than the response criterion, then the subject will respond no. But there's overlap. You see, there's overlap between the two distributions. So that's where those things we talked about earlier, like the false alarms and the correct rejection, misses and hits, that's where that comes into play. So these two things are not unrelated. Oh, one more slide before I get into that. So another term for that response criterion is beta. Beta is another term for the response criterion. And I already mentioned that it's affected by it actually can be affected by a variety of things. It can be affected by the subject's knowledge of what the likelihood of a stimulus is going to be. So for example, it could be if the tester said, you're going to hear of all the presentations I give you, say I'm going to present 100 trials to you, you're going to hear tones on 20% of the trials. If they know that in advance, that will affect their response behavior. Or I mentioned if your wording, your choice of wording, like I mentioned my example with pure tone audiometry, that will affect beta. That will affect the response criterion. You could provide them financial incentives. So I'm going to give you a nickel for every correct response, and you're going to lose 3 cents for every false alarm that you give me. That we don't see as much in kind of audiology and hearing science, but if we're looking at psychology studies, that would be very, very common to do something like that. And so if there's an incentive, that's going to affect response behavior, right? They're going to have their own, they're going to balance that in their head in a variety of ways. Maybe it's going to cause them to be a little bit more liberal about the responses because they think on average that's going to give them, more money. So these different things can affect beta, can affect response criterion. Sometimes you want them to affect response criterion. I mean, if we talked about the monetary incentive, you wouldn't accidentally have that in a study. You would only do that intentionally for whatever reason. And there are reasons, but I'm sure it depends on the exact nature of the question that's being asked. You might tell them you're only going to hear the tone 20% of the time, maybe for a particular reason, because you want to standardize. You want every subject to have an understanding of what that percentage is, so that the response criterion has shifted in a certain direction for whatever reason. So there are reasons why the tester might let the subject know that or give the subject that information. Okay, so let's go back to the overlap that I was mentioning before. So when we have this, we know that D prime represents the separation between the two probability density distributions. But we see that there's overlap between these distributions. And those are representative of the things we don't like, right? The overlap here, when we look at the response criterion is kind of the cutoff between misses and false alarms, right? Because it's also the cutoffs between yeses and nos. On the left side, we have the nos. Those are our misses, right? We have the stimulus being presented, but they didn't hear it. They said no because there wasn't enough stimulation. It wasn't high enough intensity, so they said no, but there was a tone presented, and they missed it. Over here, false alarms. There was no tone. There was no tone being presented, but yet they responded yes, because apparently there was enough energy to exceed the response criterion, and they said yes. So we can look at false alarms here. You could potentially look at the magnitude area under the curve, right? If you look at the area under the curve, you can calculate that using calculus, and you could determine what the value for this particular misses and a value for the false alarms. And I'm sure you'd come up with misses has a is a larger value than the false alarm rate. You can visually see that it's a larger area that's shaded in. And you can also look at area under the curve for correct rejection and hit. We're not going to get into that in great detail, but you can kind of see what do you want when you have two probability density distributions? Do you want to have them close together or far apart? Yeah, exactly. And you want it far apart so you can minimize any misses or false alarms. So I realize we're talking about this signal detection theory in the context of psychoacoustics, but this is quite applicable to any diagnostic test you're using. I know you talked about this in clinical audiology. You could talk about it in terms of tests that are able to diagnose brain tumors or breast cancer or whatever. You can think of these distributions in the same way. Misses and hits and false alarms and correct rejections. So that's where we talk about sensitivity and specificity. So even if you're applying this kind of idea to a test of retrocochlear dysfunction, like acoustic reflexes or something like that, the problem is if your false alarm rate is too high, then you may no longer have a good test, right? Because then you're over-referring people. And that's a very subjective decision when you talk about what is good enough for a test based on false alarm rates and things like that. But there is even an even better way to quantify this. There's a better way to quantify this that comes out of this idea. There we go. Oh, before I get there, and here are just a few examples of some other distributions where you can see there's a direct relationship between hit rate and false alarm rate. So as hit rate goes up, false alarm rate goes up. As hit rate goes down, false alarm rate goes down as well. And so what's the thing we're changing here? What are we changing between these three figures of probability density functions?
False alarm
The
and miss.
criteria.
Well, those are changing as a result
The
of
criterion.
exactly beta. We're changing the response criterion. So we can see that D prime, or the separation between those two distributions, is held constant. We're changing the response criterion. So that if you want to think about this in terms of tests, like a diagnostic test, like I was talking about a moment ago, the same thing could be held. You could say the same thing about that. Say, for example, you have two distributions, and you have one distribution which represents no, there's not a brain tumor, and another one that says, yes, there is a brain tumor. The one on the right says there's a brain tumor, one on the left says there's no brain tumor. If you move the response criterion left or right, or your cutoff, I guess, in that kind of test, then you're either going to, say, for example, let's talk about, I don't know, acoustic reflex thresholds again. What is the referral criteria for detection of retrocochlear dysfunction, right? You could set it to be very liberal, like if they're missing even one acoustic reflex is absent, then you might refer them or something like that. And then you're going to be getting a lot. You're going to have a pretty good hit rate, but your false alarm rate is going to be through the roof. Okay? Or you could change your criteria and your cutoff to be, well, I'm only going to refer them if all three acoustic reflexes ipsilaterally and all three contralaterally, if they're all absent. Okay? Well, then your hit rate's going to lower, but so is your false alarm rate too. And so there has to be, it would be nice if there was a way to decide what the best compromise would be between those. And there is a way. That brings us to receiver operating characteristics, ROC curves. So we can see this is the same kind of curve we saw earlier. It's a few slides ago. I had this one up, and we saw the only difference between these two is D prime. It's a greater separation on the top versus the bottom set of curves. We can see here what we could do is we could look at three different betas, or three different response criterions here. So if we focus for a moment on the top curves here, where we see a D prime of 2, that's going to be 2 is this very top line ABC. Okay. We want to see what is the effect of false alarms and how are hit rate and false alarms affected by shifts in our response criterion, given we know that there's a D prime of 2 here. We can see if we have the response criterion square in the middle, we can see where our hit rate is in relation to our false alarm rate here, right? If we shift that response criterion over to the right, A, that makes it a bit more conservative. Our hit rate goes down, but so does our false alarm rate. If we had shifted that response criterion to the left instead, we can see our hit rate goes way up, but so does our false alarm rate, right? And say, for example, we do the same thing, but this time we do it with a different D prime value. We have a smaller separation between the two curves. Smaller separation between the two curves, meaning we have greater overlap, right? We saw that misses and false alarms are what is represented by the overlap between the two. The overlap between the two represents misses and false alarms. And so we have greater overlap. So what typically happens here, the same exact points, E, D, and F, we see the same pattern is true for D prime of 1. The only difference that we see is that in magnitude, everything is kind of shifted towards the lower right corner. The ideal test would have the points as close to the upper left corner as possible. So that's typically how you figure out what is the best combination, what would be the best response criterion for best response criterion, or if you're talking about a particular diagnostic test, what is the best cutoff for me to use? It's whatever falls closest to this particular area. There's other ways to do it as well, but that's kind of the general idea. Does that make sense? The reason we have the lower hit rates and the greater false alarm rates for the D prime of 1 compared to 2 is because we have greater overlap. Those are directly related to one another. So if we have a smaller D prime, we're going to have a curve, say we have a D prime of 0.5 instead of 1, the curve is going to fall between D prime of 1 and D prime of 0 there. So if you have a D prime of if you have a D prime value of 0, what does that represent? What is a D
They're
prime?
like completely the same, the curves.
Yeah, with chance, though, is what it is,
Oh.
right? Because if we're talking about a binary decision where you've got yes and no, our chance is 50%. And so that means the test is garbage. You'd never want to do a test that has a D prime of 0 because it would be just as effective as flipping a coin.
Would they look the same though, the curves on would they be overlapping in the picture?
Can you ask that in a different way? I'm not sure what you're asking.
Like in the first one, D prime is 2,
Yeah.
and they're further apart, and then D prime is 1, and they're a little closer. So if D prime was 0, would the two curves be like completely on top of each other?
We already have a D prime of 0, though.
I know in that picture.
Oh,
Yeah.
on the left,
Yeah.
on the left. Oh, yes, I'm
Yeah.
sorry. Yes, they would be completely on top of each other because there'd be no separation. Yes,
Okay.
yeah.
Yeah, sorry.
I thought you were talking
I'm
about
sorry,
that
I couldn't
one.
ask that better.
No,
I
that's
didn't know how
fine.
to say it.
Thanks for the visual clarification, Megan. All right. So yeah, here, same idea here. The less overlap we have between the two curves, you can see the closer to the 50%, false alarm rate, 50% hit rate we have. So the greater the overlap between these two functions, the harder it is to distinguish noise from signal plus noise. So that's just another example. Don't need to go into that too much depth. Okay. So we have we can use these yes/no methods in psychophysics. I'm not entirely sure why they had a section on it here. I thought it was covered pretty well in the last chapter. But for the yes/no method, one thing I mentioned today that I didn't last time is you could call that a single interval force choice if you want to. I haven't seen anybody use the abbreviation of 1IFC. I haven't seen anybody use that. But you can call it a single interval force choice. I think that's a good way to describe it because there is a specified interval. That interval may be signaled to the particular subject by either a light being emitted, a tone being presented to let you know that the interval is about to start. But there is a predefined interval. And you say, for example, yes, no. You could say same, different. So in that kind of yes/no method, where you're asking somebody is the tone present, the tester might manipulate the intensity of the tone. And another one is tone. If you're asking the subject, is the tone the same pitch as the comparison tone? So is the tone that I'm presenting to you right now, is that the same pitch as the comparison tone, or is it a different pitch? Or you could do this with a speech perception study where you're presenting two different speech sounds, like a minimal pair that's only different in voicing, like P and B, and the independent variable might be the tester is going to manipulate the voice onset time of that token, like pa and ba. So that's the yes/no method that you could use in the theory of signal detection. I'm guessing the reason they're talking about this is it's a kind of a binary yes/no. Well, not exactly sure why they're talking about it in here when they've already talked about it. But otherwise, and you could also use these two-interval or the n-interval force choice methods. Two-interval force choice is probably the most common, but again, you could use whatever number you want in there. You substitute whatever number you want to use, a number of intervals for n, so 2 or 3 or 4 or 5 or 6 or on and on. There's going to be practical limits to that you probably don't want to exceed. And if you want to visually compare the yes/no procedure versus the two alternative force choice procedure, you can see that each of these kind of light gray boxes represents the interval, right? You can call it a trial, I guess, but I would I'm sorry, that's not an interval. Each box represents a trial, yeah. And the each, well, I guess you could call it interval. Well, each block here for the trial, you can see that there was one presentation. Either the tone was there or it wasn't there. Tone was there or it wasn't there. And then down below, you have 2 intervals in there. Tone was, when you have 2 intervals under that 2 interval forced choice, the tone is going to have to be in one, but it won't be in the other, right? There's no way it's going to be in both, and it's not going to be absent from both. So you're going to have a circle on one, X on the other. X would be there is no tone present. Circle would mean, yes, there is a tone present. And so say, for example, you have intervals being visualized as left and right. Maybe, for example, on the screen, and a lot of times there's a computer screen involved, they might say interval 1, which would be on the left part of the screen, interval 2 on the right side of the screen, and you might select L, I choose L has the tone, or you might select R, I choose R has the tone. So here, 2 AFC, you can see the first trial, the tone was on the left. Second trial, tone was on the right, or really it was the second interval, really. Third trial, tone was the second interval. Fourth trial, tone was the first interval. I know it's kind of weird that way. I might have been adapting this from a psychophysics that was visually oriented, but I thought it made sense to me to do it that way. It sort of, but you can kind of see side by side. I liked it because you can see how the number of intervals, I guess, yeah, number of intervals sort of is represented that way. And you have confidence rating methods, and this is going to be where you ask the patient to tell you how confident they were in their response. Say, how confident were you that the signal is present? I'm 60% confident. I'm 80% confident. And so if you do this, you're able to get more data from the same study, and you can use this to for further analysis. So it can kind of give you an idea of the subject's response criterion as well. I haven't personally read a study where they've used that and employed it, but it makes sense to me. And I think that's all here. Any questions for today? No?